So a Gantt chart is a bar chart and illustrates a project schedule. And it is used to represent the timeline of the project or multiple projects and displays the tasks or activities, their duration, and the dependencies. In software development, it is often used to track the progress of building features, with each task or activity representing a step in the development process. The horizontal axis of a Gantt chart represents time, and the vertical axis represents tasks. In this program, we aim to convert the components of a Gantt diagram into a JSON representation. I am tackling the problem of representing a set of features and their relationships in a structured JSON format. The goal is to take data that details the start and end dates, program ID, progress status, assigned team, and parent-child feature relationships, and convert this into a JSON structure. This is especially useful for creating Gantt charts that visualize the timeline and hierarchy of features within a program. So you can see an example here. This is the extended example, and we've got the start date, end date, the program, the status, the team, and this one, the parents is null because it's the top one. And then this is the child, which is a productivity suite. And then this one has this child email. And email, you can see that it has two features or sub features or two children email search and filters. And what we want to do, we want to have a text data like this and convert it to a structured JSON, as I said. So first we have this, and then sub features are the children that we have to fill them. And then we have email that has two children, email search and email filters. And this is going recursively because email search and email filters might have their own features. So the input crate in our repository is responsible for defining the input structs and implementing the required traits for reading and parsing the input data. The crate contains two main structs, ingester and raw feature. Now we're only looking at the ingester, this one. And the ingester struct has a single public field features, which is a vector of raw features. Ingester implements the try from trait, which allows converting an instance of buff reader, where R implements the read trait, into an instance of ingester. So this is implementation. We go from buff reader, as I said, to an ingester. So the implementation of the try from trait for ingester reads lines from the buff read using the read line method from here, and it removes the trailing new line character, converts the line to raw feature using the from string method, and pushes the raw features to the feature vector. So the pushing is happening here. So features an empty vector we start, and then we read line by line, and then after some conversion and pushing, we're going to fill this features vector. So the reason we use wide reader, the read line instead of iteration with the lines with map, is because the latter allocates a string for each iteration with a loop. With a loop, we can instead use a string buffer that is allocated once and cleared after each loop. And it's just like efficiency thing. And if we go, then we have here this error that we define a type. If any errors occurs during the reading or conversion process, the implementation returns an error variant of the result, with the error being of type crate errors program ingester error. And this is somewhere defined. So the raw feature struct contains 7 fields, including ID of the node, parent ID, program ID, progress status, which is complete or in progress, assigned team, which generates the feature and start date and end date. And we've got this. In the implementation of raw feature, we've got the is root function, which gives a Boolean. And if a parent ID is actually set to null or none, then it is a root feature. We saw this in the example too. And then we've got the implementation of try from, and from string, from str traits for the raw feature. The try from implementation allows creating a raw feature instance from a string. So if we've got a string, then we want to, with this function, we want to convert it to a raw feature, which results in self or self error. And error is from this type program ingester error. Right, in the previous slide, we used this method. Now we're going to implement it. The first thing that we do is we have to import a string S, and we trim it and split it into a vector of string slices, which are called parts. And we use the split method, as you can see it here. And the separator is actually space. And then the second part that we do, we have to make sure that the string is valid. In order to do this, we'll make sure that we have 6 parts. If you don't have 6 elements, the code returns an error indicating an invalid input string. So we check this, otherwise we give this error. And the next part is we get the last part of the elements, and then we have to separate it again. We have to split it into 2 parts, and we use this separator here, the separator. When we use the separator, then we have to check if we have 2 elements. The code returns an error indicating an invalid input string if we don't have 2 elements. So this is, again, another check, for like another validation check. I'm going to go back to this slide again and show you the input. This is the input that we're actually splitting. So we get like one line of this as a string. We split it with the spaces in between. And then we get 1, 2, 3, 4, 5, 6. And the 6th part is actually 1 because there's no space between. And then the last part, we get it and we split it again with this separator, and it has to have 2 elements. So that's what we've done so far. As you can see, I'm still going on with the implementation of from str method. And this is the last part. We've seen the previous part of the code. In this part, we're returning, and we're returning raw feature, which has these fields. And these fields are actually calculated here. So we have extracted feature IDs. We get the last one, unwrap it into owned and into. Unwrap means it has to exist. If it doesn't, then panics. To owned turns it to an owned variable, and into it turns it to like from one type to another. And parent ID, again, we have to get the first one. After unwrapping into owned, we check if it's null, then we turn it to or convert it to none. If it's an ID, then we give that ID. All right, now it's time for start date and end date. These fields are parsed using datetime parse from RFC 3339, which is a method to parse a date string in the RFC format. Parts.first.unwrap.to owned and parts.get1 unwrap to owned get the first and second elements from a collection parts and convert them into strings. Program ID, progress status, assigned team. These are the last fields, which are directly taken from the parts collection and specific indices and converted to the appropriate types. Before I mention any details of this code, I just want to emphasize again on the parent-children relationship, which is nested, because each parent could have a list of children. So, and each child can have a list of children too. So it's a nested one. And that's the reason that we have to think in this way quite recursively. So everything that we do from now on, it could be recursive, because each feature can have sub-features. The feature data and children struct holds 2 pieces of data. Feature data, which is an option of reference to a raw feature struct. It's an option because it is only updated to some when the data is found. This means that feature data could either contain a reference to a raw feature instance or it could be none, indicating that there is no raw feature instance associated with the struct. And children is a vector of feature ID values. This is a list of child feature IDs that can be used to look up related information in the feature map. So we've got these 2. I mentioned feature map. Feature map is here. And feature map is a type alias for a hash map. Hash map data structure. A hash map is a collection of key value pairs. You can see it here too. We've got the key, which is feature ID, and we've got the value, which is feature data and children. And so where the keys here are of type feature ID, as I said, and the values are of type of feature and data children. This type alias makes it more expressive and easier to use, as a type feature map is more meaningful and understandable than the underlying type hash map. And then you might ask yourself, what is this A? A is actually a lifetime annotation, single quotation A. And those lifetimes are a way of expressing the relationship between references. They ensure that the references are used in a safe and correct way by preventing references from pointing to data that has been dropped. So if we go back to our previous slides, we have seen this type error which is program ingester error in multiple places. When we implemented ingester here, this type error, and also in the implementation of rule feature, we have seen this type, program ingester error. So now it's time to actually define this type. So in this code snippet, we define an error enum with the use of this error crate. And this error crate allows us to handle custom errors as well as wrapping errors produced by other crates to make using that question mark possible. And you can see that the error trait has this derive error and debug attribute, this part. And this part, as I said, this is actually from the this error crate. So the enum has 3 variants. So the first variant, which is invalid program input. The variant is used when the input to the program is not valid, and it carries a string message describing the error. And then we have the second one, which is invalid timestamp. The variant is used when the timestamp and the input cannot be passed, and it carries an underlying error of type chrono pass error. And the last one, the third variant of this enum, is IO error. This variant is used when an IO operation fails, and it carries an underlying error of type IO error. So the feature struct. The feature struct represents a feature in a software development project. It has the following fields: ID, which is a string identifier for the feature; progress status, could be in progress or finished, or any sort of progress status that it has; assigned team, start date, end date, and subfeatures. And subfeatures are actually a vector of feature. A feature is an object representing subfeatures of the current feature. This struct is decorated with derive, debug, serialize, and clone, which uses Rust's derive macro to automatically generate implementations for the debug, serialize, and clone traits. This means that instances of feature can be debugged, serialized, which is conversion to a format like JSON, and cloned, duplicated. The line assertive rename feature that we have here. So this one uses asserters setter attribute to specify that the ID field should be renamed to feature when serializing or deserializing instances of feature. The line setter serialize with ordered features, this part. So this one uses setter's setter attribute to specify that the subfeatures field should be serialized using a custom serialization function named ordered features. And this is a custom logic to be used when serializing the subfeatures field. So we just talked about the custom serializer here, ordered features, and now we want to see the function. So ordered features takes in a slice of feature objects, value, and a serializer. The function sorts the input slice of feature objects by the start date field and then serializes the sorted slice using the provided serializer. The function returns a result type that represents the outcome of the serialization process. If it is successful, the result will contain the serialized value, which is SRK. If it's not successful, then an error occurs during serialization. The result will contain an error value of type S error. And this function uses the where clause to specify that the type of the serializer here must implement the serializer trait. So this is the where clause. And this allows the function to be used with any serializer that implements this trait, making it more flexible. The method toOwned is a method that creates a new owned value. It's a deep copy from a borrowed value. When we do toOwned, this is a deep copy. And so this is a borrowed value, like such as a reference. In this case, the method is used to convert the input slice of feature object's value into an owned vector of feature objects. This is quite necessary because you might be wondering why. Because the sorting operation needs to modify the contents of the vector. and the reference to the original slide cannot be modified. By creating an owned copy, the original data remains unchanged, and the sort operation can be performed on the copy. We're doing the sort on the copy. So there are a couple of more structs that we will see in the upcoming slides. Program and also program graph. Program has two fields, ID and root. Root is of type feature and ID is a string. And program graph, which has programs as a field, which is a vector of program. And then as we've seen this type of serialization or custom serialization, that we have a function before we have the same thing here for program graph too. And this is a function for it, exactly with the where clause that has to implement the serialization. And then the same, very similar functions before that were seen. The only thing is we use program.row.startDate for sorting. And at the end, we serialize this value. The reason that we serialize the value is because we want to convert it to JSON. So the partial EQ implementation of a program graph sorts the programs with the root start date before checking for equality here. Here you might be wondering what all these structs are. So I've got an explanation for you. The rule feature was the struct that we were reading straight from the text data. Exactly, we were just splitting the string into multiple fields. And then we had, for each child, we had the parent ID, program ID, and some other fields. Then if we go to slide 8, we defined another struct, which was a feature. In this one, instead of having the child, we have the parent, and we've got the sub-features. So we're not only seeing the some of the fields of that particular rule feature, we are seeing the sub-features or children of that feature too, as a vector of feature. Now I'm going to slide 10. And here you can see that program has the root as a type feature with those sub-features. And then the next one, program ID, program graph, has the same thing, which is a bunch of programs, which is a vector of program. So what we want to achieve here, we want to read from the text data and then have converted to the struct format of type rule feature, then go from rule feature to program graph. Then most of the serialization is done for us. Let's have a look at the transformation from rule feature to program graph. So as you can see, this is our text data, and we have shown this before. We read each line and split the string into multiple fields. Then what we have is this rule feature, this vector of rule feature. And then each rule feature has the ID, parent ID, and some other fields like status and other things, start date, end date. So for the type conversion that I said, we have to implement the from trait or this from block, which is actually the implementation of the from trait. And then next we are going to create this mappings. And this mappings is a container to hold feature data and the relationships. The code then iterates through each rule feature in the input vector. For each feature, it checks if it already exists in mappings using match. If the feature is present, it updates its feature data here with the sum. And if not, it inserts a new entry with the feature data and an empty list of children. This process is there to help us have all features properly added or updated in the map with the respective parent-child relationships. Bear in mind that we have a placeholder for the parent-child relationship here with this vector of empty, but it hasn't filled yet. So we're going to do this next. But before that, have a look at the outcome of this step. So we've got each parent, and each parent has its own children, but the children, they've got empty vectors. And then the next step is what we're going to do. So in this step, this snippet handles the establishment of parent-child relationships within the mappings by checking if the current feature has a parent ID. If it does, it attempts to update the parent's entry in the mappings. If the parent already exists in the map, the snippet adds the current features ID to the parent's children list. So we add this to the list of children. And if the parent does not exist, it inserts a new entry for the parent with no feature data, but initializes the children list with the current features ID. And then we get from this previous one that we had the children vector of empty. We run this part, and then we get this one. So now each of them has the vector of the children. After creating the mappings with the loop over the rule feature of the vector of rule features, then we have to create the roots. It's just one small step that we're doing this. And this is just to iterate over each value in the mappings after mappings are complete and check if the feature data is present. If feature data is available, then we use feature data as root to determine if the feature is a root feature. Root feature means a feature with no parent. If feature data is absent, then the feature is not considered as a root. And the result of this is a collection of root features, which are used in the next step to construct the final program graph. So here we create a program graph with this line. This is the initialization. And then what we do is we process each root feature to build the program objects. For each root feature in the roots collection that were created before, the code checks if feature data is present. If it is, then it creates a program with the root features data. Recursively resolves its subfeatures using resolve subfeatures here. And then we're going to get back to this and see why it is recursive and how it could be recursive. And the constructed program now is then added to the graph.programs list. And if it's missing, if there's a missing, then we've got a to-do here. So this is not implemented. So this slide shows how we build this program graph using resolve features recursively. So this slide shows how we build this program graph using resolve features recursively. So with this command line interface here to ingest data, build a graph and output it to the terminal. So the code imports essential modules for the program, standard library components for environment variable access, file handling, buffered I/O operations. And we also import some types from our own crate, which is program ingester. Those types are ingest and program graph. And then we also have some of the extensions from the tracing subscriber to enhance our logging and tracing capabilities. Here is our main program. And then the first thing that we do is the setup, which is a tracing subscriber setup to log messages. The log level is either set by the Rust log environment variable or falls back to the info if the environment variable is not set. And then next step in our main program is here. So we read CLI arguments. The command line arguments passed to the program are collected into a vector of strings. If there are more than 2 arguments, a warning is logged that the additional arguments will be ignored. Let's go back to the main program to see where we are. Then see the next part. And in the next part, we're going to see how to build the ingester. So the ingester reads input from either a file specified in the command line arguments or from std in. If no file is specified, then we use std in. The ingester is built using the ingester struct that I saw before, which provides a method to parse features from the input source. Now let's go back to the main program again to see where we are. And then next we're going to build a graph in here. So the program graph is output to the terminal using the println macro and the debug format. I usually create some examples to show how to use the code or the library in various ways. So in program ingester, I have folder examples. And then the main example that I have a simple tree. I've got another one, hash map iterations. This is just for the testing how hash map works. You can check that out. But the main one is simple tree, and we're going to run it. Cargo run -- example simple tree. And you can see that this is the outcome of simple tree.